Hello all, welcome to the high speed designs tutorials. So in this video we will talk about impedance discontinuity. So again, this is a very familiar topic, but what new are we going to talk here? So let us see. Okay, let us assume we have a driver, okay, which is driving a channel, and then there is a receiver. This is a common topology, right? In the designs. So we do have a high speed signal that is coming out and then going to the receiver. Now this particular channel that we see, we say that this should be having a common impedance across the entire length of this channel. Now there are practical scenarios where the impedance might have to vary a little at some places. Ideally, the impedance should not vary. But what happens is, let us assume we have a board, okay, and then we have a driver somewhere placed. Driver is nothing but a part of an IC, right? And then there is one more IC that is placed. Let us assume they are both placed on the top itself, okay, and while routing, let us assume there are some other traces that are routed nearby. So here we might have a fixed length, fixed width, and when we come nearer to these signals, we might reduce the width of this signal a bit, and again come back to the actual width that is required, whether it be 50 ohms or whatever. So this small patch, there's a big doubt among the engineers whether this short patch can be routed with a different impedance or not. The practical problem here is when we run this with the same with 50 ohms, there might be some coupling from here and here to this signal. So the design engineer might ask a PCB layout engineer to have the width reduced. Now, can it be reduced or not? That's the biggest point. So in high speed designs especially, the important point is the important parameter is the rise time. Okay, this is what plays a critical role or determines what need to be done on a design. Now every trace that is routed between the driver and the receiver will have a delay which can be called a transmission delay. Okay, so this transmission delay causes the signal to arrive at a later time than the introduction into the channel. So this is another important parameter. Rise time is another important parameter. So now, as we said, the small patch, right? The small patch, let us assume the length is L. Okay, if the length of the small patch is much lesser compared to the transmission line, signal rise time, then this can be done. This can be blindly implemented in the PCB design. So that short path, you can definitely have impedance continuity and still see a proper signal at the receiver with much lesser reflections on the channel. Okay, so this scenario. Now let us assume I have 1 nanoseconds. Okay, 1 nanoseconds of rise time. If at all I have 1 nanoseconds of rise time, then my length must be 1 nano inch. Okay, so this is the impedance discontinuity that is allowed. So now what happens is, in practical scenarios, this is not possible, right? So practically this scenario is very less, right? So that is the reason why in general we commonly treat that the line should have a continuous impedance, and then indirectly we eliminate any discontinuity in the impedance and then route the traces. So definitely possible to have small deviation impedance, but practically difficult to achieve as we go in higher speeds. But definitely, if the rise time is lesser than this, okay, and if the length becomes practically achievable, then it is possible. Then again, it comes under the criteria of not a high speed signal, a low speed signal, right? So hope we can give some input on impedance discontinuity. Please post your questions. Um, Please let us know if there are any corrections in this video. Thank you.